Before we get into this, do yourself a favor and subscribe. Because what our sun is doing right now is something it only does for a brief window every 11 years or so. And if you understand what is happening up there, you will look at the sky and at your own technology down the road. In a completely different way. For the first time in over a decade, the sun has reached a peak in its activity that it simply does not reach most of the time. More sunspots, more flares, more powerful bursts of energy hurled out into space. This is not a disaster, and I'm not here to frighten you, but it is a genuinely important moment in the life of the star that makes life on Earth possible. So stay with me, because by the end of this, you will understand exactly what the sun is doing, why it matters for all of us, and what it means for the months ahead. Let us begin with the most basic truth about the sun, because everything else flows from it. The sun is not a solid, calm ball of light. It is a colossal sphere of superheated gas, so hot that the atoms themselves are torn apart into a state of matter called plasma. Deep in its core, the sun is fusing hydrogen into helium, releasing unimaginable amounts of energy, and that energy works its way outward over hundreds of thousands of years before finally bursting free from the surface as the sunlight that reaches us in just 8 minutes. But the sun is not just a steady lamp. It is a churning, turbulent magnetic monster, and its magnetic field is the key to understanding everything we are about to discuss. Here's the thing about that magnetic field. It is not fixed. It is constantly being twisted and tangled by the motion of the plasma inside the sun. Because the sun is not solid, different parts of it rotate at different speeds. The equator spins faster than the poles. Over time, this uneven rotation winds up the sun's magnetic field like a rubber band being twisted tighter and tighter. And as that magnetic field gets more and more tangled, it produces the visible signs of solar activity that scientists have been tracking for centuries. The most famous of these signs is the sunspot. A sunspot is a region on the surface of the sun where the magnetic field has become so concentrated and intense that it actually blocks some of the heat rising from below. Because that spot is slightly cooler than the surrounding surface, it appears darker to us. But do not let the worse cooler fool you. A sunspot is still thousands of degrees hot. It only looks dark by comparison to the blazing surface around it. And these sunspots are not small. A single large sunspot can be many times wider than the entire Earth. When you look at an image of the sun covered in sunspots, you're looking at regions of incredibly powerful, twisted magnetic energy, and each one is a potential site for an explosion. Now here's the pattern that scientists discovered a long time ago, and it is the heart of this whole story. The number of sunspots on the sun is not constant. It rises and falls in a cycle that lasts, on average, about 11 years. At one point in the cycle, called solar minimum, the sun can go days or even weeks with almost no sunspots at all. Its face is quiet and clean. Then, over the following years, the activity builds. More and more sunspots appear. The sun grows stormier and more violent, until it reaches the opposite extreme, called solar maximum, when the surface can be peppered with sunspots and the sun is unleashing flares and eruptions far more frequently. Then, gradually, it all winds back down toward another minimum, and the cycle begins again. This 11-year rhythm is called the solar cycle, and scientists number each cycle as they track it. We are currently in the cycle that researchers labeled as the 25th since detailed record-keeping began. And this is exactly why this moment is so significant. The sun has now climbed to the peak of this cycle to solar maximum. That is the something it has not done in over a decade, because the last time the sun was this active was during the peak of the previous cycle, around 11 years ago. What makes it even more noteworthy is that this cycle has turned out to be stronger than many scientists originally predicted. Early forecasts suggested it might be a relatively weak cycle, but the sun had other plans. It has produced more sunspots and more powerful activity than those early predictions expected, which has taken even some experts by surprise. So what actually happens when the sun reaches this peak of activity? To understand that, you need to know about the three main types of solar events that increase during solar maximum. The first is the solar flare, the second is the coronal mass ejection, and the third is the enhanced solar wind and the geomagnetic storms it can cause. Let me walk you through each one, because together they explain why solar maximum matters for the technology that runs our modern world. A solar flare is, in simple terms, a sudden, intense flash of energy released from the sun's surface. It happens when those twisted, tangled magnetic field lines around a sunspot suddenly snap and reconnect into a simpler arrangement, releasing an enormous burst of energy all at once. Think of it like a stretched rubber band that suddenly breaks. All that stored tension is released in an instant. A large solar flare can release as much energy in a few minutes as billions of nuclear explosions, and it sends out a blast of radiation, including intense bursts of ultraviolet light and X-rays. This radiation travels at the speed of light, which means it reaches Earth in about 8 minutes. the same time as ordinary sunlight. When it arrives, it strikes the upper layers of our atmosphere. Now, our atmosphere protects us on the ground from the harmful effects of this radiation, so a solar flare is not going to hurt you directly as you go about your day. But it can have real effects on technology. That sudden burst of X-rays can disturb the upper atmosphere in a way that disrupts radio communications, particularly the high-frequency radio that aircraft and ships rely on. During a strong flare, pilots flying over certain regions can temporarily lose radio contact. So even though you would never feel a flare yourself, it can ripple through the systems we depend on. Scientists actually sort solar flares into categories based on their strength. And it helps to understand this because you will often hear these labels in the news. The classes are named with letters. The smallest significant flares are called C-class. Stronger ones are called M-class, S, and the most powerful are called X-class. Each step up that scale represents a flare roughly 10 times more powerful than the one below it. So an M-class flare is about 10 times stronger than a C-class, and an X-class flare is about 10 times stronger than an M-class. During the quiet years of the solar cycle, powerful X-class flares are rare. But during solar maximum, M, when the sun is covered in active sunspots, these strong flares become far more common. This is one of the clearest ways to see that we are at a peak in the cycle, when the sun starts producing frequent M-class and X-class flares. You know it has entered its stormy season. The strongest flares are the ones capable of the biggest effects on our technology, which is why scientists pay such close attention when a large, active sunspot region rotates into a position where it is facing directly toward Earth. The second type of event is the one that can be even more consequential. It is called a coronal mass ejection, often shortened to CME. While a solar flare is a burst of radiation, a coronal mass ejection is something more physical. It is a MI, massive cloud of the sun's own material, billions of tons of plasma actually launched off the sun and out into space. Imagine the sun belching out a gigantic bubble of magnetized gas, hurling it across the solar system at speeds that can reach millions of kilometers per hour. Unlike a flare, which arrives in minutes, a coronal mass ejection takes longer to reach us, usually somewhere between 1 and 3 days, depending on how fast it is moving. And here is the crucial part. If that cloud of solar material is aimed at Earth, and if it collides with our planet's magnetic field, it can cause what we call a geomagnetic storm. This brings us to the third piece of the puzzle. Earth is protected by its own magnetic field, an invisible shield generated deep in our planet's molten core. This magnetic field, called the magnetosphere, surrounds the Earth and deflects most of the constant stream of particles flowing from the sun, which we call the solar wind. Most of the time, this shield does its job quietly and we never notice. But when a powerful coronal mass ejection slams into the magnetosphere, it can compress and disturb it violently, causing a geomagnetic storm. During such a storm, energy pours into the upper atmosphere near the poles, and this is what produces one of the most beautiful sights in all of nature. The auroras, the northern and southern lights. Those shimmering curtains of green, red, and purple light that dance across the polar skies are the direct, visible result of solar particles interacting with our atmosphere. During strong geomagnetic storms at solar maximum, these auroras can become so intense that they are visible far from the poles, in places that almost never see them, sometimes reaching regions much closer to the equator than usual. But geomagnetic storms are not only beautiful, they can also be disruptive, and this is the practical reason scientists watch solar maximum so closely. When a geomagnetic storm energizes the upper atmosphere, it can affect a whole range of technologies that our modern civilization depends on. Let me give you some concrete examples, because this is where it becomes real. Satellites orbiting the Earth can be affected, because the storm causes the outer atmosphere to heat up and expand, which increases the drag on satellites in low orbit and can pull them off course or shorten their lifespan. The signals from navigation satellites, the ones that power the maps on your phone and guide ships, aircraft, and even farm equipment, can become less accurate during a strong storm because the disturbed upper atmosphere distorts the signals passing through it. Radio communications can be degraded. And in the most extreme cases, geomagnetic storms can even affect power grids on the ground by inducing unexpected electrical currents in the long transmission lines that carry electricity across countries. In rare, severe events, this has been known to cause equipment damage and even blackouts. The most famous example of just how powerful a solar storm can be happened long before we were so dependent on technology. In the 1850s, an enormous solar storm struck the Earth, an event now known as the Carrington event, named after the astronomer who observed the flare that caused it. Back then, the most advanced electrical technology in the world was the telegraph system. During that storm, telegraph systems across Europe and North America went haywire. Sparks leapt from the equipment. Some operators received electric shocks. Some telegraph lines kept working even after their power was disconnected, running on the electrical current induced by the storm itself. And auroras were seen so far from the poles that in some places people reportedly woke in the middle of the night thinking it was dawn. Now, here is the sobering thought that scientists consider. If a solar storm of that same magnitude struck today, with our world so utterly dependent on electricity, satellites, and interconnected electronics, the effects could be far more serious and costly than they were in an age of simple telegraphs. This is not a prediction that such an event is coming. Storms of that size are rare. But it is precisely why understanding and monitoring the sun's activity is so important, and why solar maximum is a period that space weather scientists watch with such focus. Now, let us talk about how scientists actually monitor all of this, because the technology involved is remarkable. There is one more group of people for whom solar activity is a very real and immediate concern, and that is astronauts. Out in space, above the protection of most of Earth's atmosphere, the radiation from a powerful solar flare or a burst of solar particles is a genuine hazard. Astronauts on space stations have shielded areas they can move to during periods of heightened solar activity, and space agencies carefully monitor the sun to warn them when a strong event is occurring. For any future missions that would take humans further out, to the moon or beyond, understanding and predicting solar activity becomes even more critical, because out there, away from Earth's protective magnetic shield, a major solar storm could pose a serious danger to the crew. This is one of the practical reasons that studying the sun's cycle is not just an academic exercise. It is essential knowledge for the future of human exploration. Even here on Earth, there are subtle effects worth understanding. Frequent flyers and airline crews who spend long hours at high altitude, especially on routes that cross near the poles, are exposed to slightly more radiation during periods of high solar activity, because those polar routes pass through regions where Earth's magnetic shielding is weakest. The doses involved are small and carefully managed, and this is not a reason to avoid flying, but it is another example of how the sun's activity reaches into aspects of our modern lives that most people never think about. There is an entire field of science called space weather forecasting, dedicated to watching the sun and predicting its behavior. A fleet of spacecraft and telescopes, both in space and on the ground, keep a constant eye on our star. Some spacecraft sit between the Earth and the sun, watching for coronal mass ejections and measuring the solar wind before it reaches us, giving us precious hours of warning if a storm is heading our way. Other telescopes photograph the sun continuously, tracking the sunspots and detecting flares the moment they erupt. When a large flare or a coronal mass ejection occurs, scientists can often estimate whether it is aimed at Earth, how strong it might be, and when it might arrive. This gives operators of satellites, power grids, and airline the chance to take protective measures, such as putting sensitive equipment into a safe mode, rerouting flights away from the poles, or preparing power systems for potential surges. This early warning capability is one of the quiet triumphs of modern science, and it is exactly why a period of high solar activity, while significant, is something we are far better prepared for than any generation before us. There is one part of the sun that deserves special mention here, because its name appears in the term coronal mass ejection, and it holds one of the great mysteries of solar science. That part is the corona, the sun's outer atmosphere. If you have ever seen a photograph of a total solar eclipse where the moon completely blocks the sun, you will have seen the corona as a faint, wispy halo of light stretching out around the darkened disk. This outer atmosphere is where those coronal mass ejections origin, and it is the region most dramatically affected during solar maximum. Here's the puzzle that has fascinated scientists for decades. The surface of the sun is roughly 5,500 degrees, but the corona above it, further from the core, is astonishingly hotter, reaching millions of degrees. This is deeply strange. Normally, the further you move from a source of heat, the cooler it gets. Move away from a fire and you feel less warmth, not more. Yet the sun's outer atmosphere is hundreds of times hotter than its surface. Scientists believe the answer lies in the sun's magnetic field, the same magnetic field that drives the whole solar cycle, channeling and depositing enormous amounts of energy into the corona. Missions have flown closer to the sun than ever before, precisely to study this mystery. And it is one of the reasons that periods of high solar activity are so valuable to researchers. When the sun is at its most active, they get to observe these processes at their most dramatic. It can help to picture the whole solar cycle with a simple image. Imagine winding up a spring or a rubber band. At solar minimum, the sun's magnetic field is relatively simple and orderly, like a rubber band at rest. Then, because the sun rotates unevenly, that magnetic field gets wound tighter and tighter over the following year, becoming more and more tangled and stressed. Solar maximum is the point where the magnetic field is most twisted and knotted, storing the most tension, which is exactly why it produces the most flares and eruptions, as all that tangled energy finds ways to release itself. Then, over the following years, the phi. Eld essentially resets and simplifies, unwinding back toward another minimum before the whole process starts over. Understanding this simple picture of a magnetic field being wound up and released over an 11-year rhythm is really the key to understanding everything the sun does during its cycle. Let me be very clear and honest here, because that honesty matters more than any dramatic framing. Solar maximum is a completely natural, normal, and recurring part of the sun's behavior. It has happened countless times throughout the sun's life, long before humans existed, and it will happen countless times more. It is not a sign of the sun dying or of anything unusual going wrong. Every 11 years or so, the sun does exactly this. The vast majority of solar flares and coronal mass ejections have no noticeable effect on your daily life at all. Most are either not aimed at Earth or are not powerful enough to cause significant disruption. So there's no reason for fear here. The right response to solar maximum is not anxiety, but appreciation and awareness. It is a chance to understand the living, dynamic star that sits at the center of our solar system. There's also something genuinely wonderful about this moment for anyone who loves the natural world. Because the sun is so active right now, the chances of seeing the auroras are higher than they have been in years. People who live at higher latitudes, and sometimes even those a good deal further south, have had opportunities to witness these lights that they might not get again for a long time. If you have ever wanted to see the northern or southern lights, a period of solar maximum is the best time to try, because the geomagnetic storms T have produced them are more frequent and more intense. It is one of the few times when the invisible drama playing out between the sun and the earth becomes something you can actually see with your own eyes. So, what does this all mean for the months ahead? Because we are at or near solar maximum, we should expect the sun to remain quite active for some time. It is important to understand that solar maximum is not a single day or a single event. It is a period, often lasting a year or more, during which activity is elevated. So over the coming months, it is entirely normal to expect more sunspots, more flares, and more coronal mass ejections than we would see during the quiet years of the cycle. Some of these will produce beautiful auroras. A few might cause minor disruptions to technology. And on rare occasions, there could be a stronger event worth paying attention to. But none of this is cause for alarm. It is simply the sun doing what it does at this stage of its rhythm. The activity will not stay at this peak forever. In the years following the maximum, the sun will gradually settle back down toward another minimum, and the whole 11-year cycle will begin again. Let me pull together the key points so you walk away with a clear understanding. First, the sun goes through a natural cycle of activity lasting about 11 years, swinging between quiet minimums and stormy maximums. Second, we are now at the peak of the current cycle, a solar maximum, which is why the sun is more active than it has been in over a decade. And this particular cycle has proven stronger than early forecasts expected. Third, this heightened activity produces solar flares, coronal mass ejections, and geomagnetic storms, which can create stunning auroras but can also disrupt satellites, navigation, I/O, and in rare, severe cases, power grids. Fourth, this is a completely natural process that poses no direct danger to you personally, thanks to Earth's protective atmosphere and magnetic field. And fifth, we monitor the sun constantly with a sophisticated network of spacecraft and telescopes, which means we can forecast space weather and prepare for significant events in ways no previous generation could. The sun has been our constant companion for billions of years, pouring out the light and warmth that made every living thing possible. And every 11 years or so, it reminds us that it is not a passive object, but a dynamic, powerful living star, going through cycles of calm and storm just as our own world goes through its seasons. Right now, it is in one of its stormy seasons. It is a moment worth understanding, worth respecting, and if you get the chance to see those auroras dancing overhead, worth appreciating for its sheer beauty. I will keep watching the sun and bringing you clear, honest updates on its activity as this solar maximum unfolds. If you found this valuable, let me know in the comments where you are watching from, and whether you have ever been lucky enough to see the northern or southern lights. Take care, keep looking up, and I will see you in the next one.